In these sections, I'd like to explain the Fourier integral. We studied how to express the function of the f is a Fourier series. Fx is expressed as a sub 0 over 2 and sigma I equal 1 to the infinities a sub I cosine I pi over px plus b sub I sine I pi over px. This is a Fourier series. And a sub 0 is calculated 1 over p minus p to the p fx dx. And a sub I is 1 over p minus p to the p fx cosine I pi over px dx. And the b sub I is 1 over p minus p to the p fx sine I pi over px dx. We'd like to substitute this equation into the each terms. Then it becomes this equation. So this is the expressions of the f with the trigonometric functions. Then we'd like to change the variables. So alpha sub I is equal to the I pi over p. So delta alpha is the difference of the alpha sub I plus 1 minus alpha sub I. It becomes pi over p. 1 over p is expressed delta alpha over pi. So 1 over p becomes delta alpha over pi. First terms. And the second terms, 1 over p is delta alpha over pi. And the inside of the cosine function, this corresponds to the alpha I. This is alpha sub I. This is also alpha sub I. This is also alpha sub I. So we could express the fx in these equations. Then we'd like to expand the interval to the minus infinity to the infinities by letting the p approaching to the infinities. First terms becomes 0 because the definite integrals minus p to the p ft dt is converged to the finite values. But first term is divided by the p. So this means first term is approaching to the 0. We don't have to consider the first terms. Then if the p is approaching to the infinities, so sigma times the delta alpha is expressed with the integrals from the 0 to the infinities dt's. So by changing the sigma to the integrals, so this is integral 0 to the infinities with respect to the d alpha. This is the functions becomes expressed as two integrals. This first parenthesis correspond to the coefficient of the capital A alpha. And the second parenthesis correspond to the coefficient of the B alphas. Then this equation is simplified by introducing the two coefficient. Function is expressed fx is 1 over pi times A alpha cosine alpha x plus B alpha sine alpha x d alphas. This is called the Fourier integral of f. You can calculate the capital A using the first equations. And for the b, you can use this calculation to find the capital b's. By using this capital A and capital B, function is expressed trigonometric functions with the integral. So we call that this is the Fourier integrals. Then I'd like to show you some example. So in the practice, we studied fx is 0, 1, 0. At x is a negative quantities 0, x, 2, and x is larger than 2. We calculate this function is expressed fx using the integrals 2 over pi, integral 0 to the infinities, sine alpha, cosine alpha x minus 1 over alpha d alpha. So as the upper limit, we choose a b. By changing the b, we calculate this integral to find out the f. So if we choose a b equals 3, this calculation corresponds to the fx, blue lines. And the original function of the f is given by the orange lines. So when the b equals 3, trend of the curve is very similar, but it's quite easy to distinguish to the two curves. And by increasing the b, two curves is approaching. And finally, if the b is 100, we have almost identical curves. The blue curves and the orange lines very close. So by increasing the upper limit of the b, we can express the function of the f using the Fourier integrals. Then I'd like to introduce a complex form of the Fourier integrals. This is the expression, first equation is the expression of the Fourier integrals. This is the cosine, sine. Then we can combine these two functions using the addition formula for the trigonometric functions. This becomes a cosine alpha times t minus x. This is equal. Cosine functions. This cosine functions is a even functions with respect to alpha. So we expand range of the integral from the minus infinity to the infinities. Because of the even functions, we should divide it by the 2's. Then we consider the odd function of the sine. This sine function is odd functions with respect to alpha. Then if you integrate of the sine functions with respect to the alpha, it becomes 0. It's actually we add the second terms, but it becomes 0. So just add these terms. Then we use the Euler's formula to combine the cosine function and the sine function to express the exponential I alpha t minus x. We use the Euler's formula to combine these two terms. Then this final expression is expressed with the integrals with respect to t and the integrals with respect to alpha. If you consider this inside of the parenthesis is a coefficient of the C alpha, by introducing C alphas, fx is expressed as these equations using the complex function of the exponential minus I alpha x. So fx is given by the 1 over 2 pi and the integrals minus infinity to the infinities C alpha exponential minus I alpha x integral with respect to alphas. And the C alpha can be calculated with these equations. This is a complex form of the Fourier integral of f. Okay, so in this session, I introduced the Fourier integrals. Okay, this is the end of this session.